Elasticity, elasticity, elongation. To understand elongation, let us imagine a rubber cord of length AB. In the figure, AB represents a rubber cord. If it is stretched to a length CD, CD is elongated position of the rubber cord. By applying two forces, which are indicated by arrow marks showing outwards, they are the forces applied outwards. These forces will elongate the rubber cord. Its original length is AB and its elongated length is CD. So its length has increased. When the length has increased, the molecular force of attraction increases. Hence, the restoring forces act inside the rubber cord. They are shown by the arrows towards AB. The arrows towards AB indicate the restoring forces which try to regain the original shape and size of the rubber cord. Similarly, if a steel wire is suspended from a ceiling, if it is suspended from a ceiling from a point O and some load is attached at the free end, then the load attached at the free end acts as the deforming force, that is the elongating force. Because of this, suppose length of this wire becomes equal to the original length is OP and the stretchy length is say OQ, that is the length has increased from P to Q, then PQ is the increased length. In this state, the deforming forces act downwards and the restoring forces acts upwards. Like this, whenever we apply forces, there are certain substances in which we notice large elongations. In substances like steel also, we notice small amount of elongation with a large force. By applying large force, we can elongate wires, steel wires. For the study of elasticity, we require the concept of restoring force. Here in this figure, I have shown restoring and deforming forces. The deforming forces are shown outwards and the restoring forces are acting inwards in the rubber cord and in the wire also. Deforming force is downwards and restoring force is in the upward direction. Like this, first we have to understand the restoring forces, because elasticity depends on restoring forces. Elasticity is dependent on restoring forces. First we have to understand the restoring forces. Depending on elasticity, we classify the substances into two categories: elastic bodies and plastic bodies. Elastic bodies and plastic bodies. A body is said to be an elastic, or a substance is called an elastic if it regains its original shape and size on removing the deforming forces. When forces are applied, deformation takes place, and when the deforming forces are removed, if the body regains its original shape and size, then it is called an elastic body. If the deformed state is retained by the body, then it is called plastic body. Examples of elastic bodies: rubber, metals, crystals, etc. Examples of elastic bodies: rubber, metals, crystals, etc. Examples for plastic bodies: chewing gum, lead solder, putty, dough, wax, wet clay, etc. To study elasticity, we define two physical quantities. One is stress, the other one is strain. Stress and strain. Stress is defined as the restoring force per unit area. The restoring force per unit area is the definition of stress. Strain is change in dimension per original dimension. Strain is change in dimension per original dimension. That is, change in length per original length in the case of longitudinal strain, change in volume per original volume in the case of bulk strain, and angular twist in the case of shearing strain. Like this, we come across three types of strains: change in length by original length, change in volume by original volume, and angular twist. Longitudinal stress and longitudinal strain. Longitudinal stress and longitudinal strain. Let us imagine a wire suspended from a ceiling carries a load. The length of the wire is say L. The load attached is say mg. The weight attached is mg. After attaching this load, the length of the wire increases. Let us suppose the increase in the length is say small e. It is represented at the right side figure. Mg represents the deforming force and F, the arrow upwards, indicates the restoring force. Of course, F is equal to mg in magnitude. Their directions are opposite. L represents the original length and the colored circle represents the deformed state of the load, and the non-colored rectangle represents the original position of the load when it is attached. And small e represents the increase in length of the wire. L represents the original length of the wire when it is not deformed. Now, we define that stress is restoring force per unit area. To understand area, if you take the cross section of the wire, the cross section is circular. A ring is shown at the center. Capital A represents the area of this cross section. So when this mg load or weight or force is acting on over an area capital A. So the restoring force is F by A, or the stress. The restoring force is F and the area on which it is acting is A, hence stress is equal to F by A. Stress is equal to F by A. Strain is change in dimension per original dimension. Here the dimension is length. So change in dimension is E, that is increase in length. Original dimension is L. Hence strain is equal to E by L. Strain is equal to E by L. So mathematically we represent longitudinal stress by F by A and longitudinal strain by E by L. Like this we study longitudinal stress and strain. Shearing stress and shearing strain. To find relations for shearing stress and shearing strain, let us take a cuboid, a cardboard like cuboid. And if a force is applied tangential to the upper layer, upper surface, suppose the right hand side figure represents the original cuboid and the left side figure represents the deformed state. When a force F is applied tangential to the surface, top surface, keeping the lower surface constant, then the top surface moves by a distance small e. The top layer displaces by a distance small e. So I have shown two positions. One is original position, the other one is deformed state of this cuboid in the left side figure. Now the angular displacement of the lateral side, the angular displacement of the lateral surface is say theta. The height of this cuboid is say h. Height of the cuboid is h. And the top surface or the bottom surface is area is capital A. The area of the top surface is capital A. The restoring force acts to the left, which will be equal to the force F applied to the right. Hence, the stress is equal to F by A. The stress is equal to F by A, tangential force by area. And strain will be equal to E by H, which will be equal to theta when theta is very small. When theta is very small, E by H will be equal to theta. E is the elongation, H is perpendicular distance. So E is change in dimension, H is original dimension. Hence, E by H is the shearing strain. F by A is shearing stress and theta is shearing strain. To obtain relations for bulk stress and bulk strain, let us imagine a ball. Let us imagine a ball, spherical ball. Suppose the rose colored circle represents a ball and the arrows represents the pressure applied on this ball. If the original volume of this ball is say V, when pressure is applied on all sides and its volume decreases, and say the new volume is represented by the brown colored circle, then the change in volume is delta V and the final volume is V minus delta V. Right side figure represents the change in volume. Rose color represents original volume and it is change in volume. Right side one is change in volume. The change in volume is delta V. Now we know that the pressure is the force applied per unit area. The force per unit area is called pressure. Hence, the pressure becomes equal to stress. Because pressure is force per unit area, so stress is nothing but pressure. And strain will be delta V by V. Delta V is change in volume and V is original volume. So change in dimension is delta V, original dimension is V. Hence, change in dimension by original dimension, delta V by V is strain. This strain is called bulk strain. The stress or pressure is called bulk pressure, bulk stress, and the strain is bulk strain. Like this, we find the relations for bulk stress and bulk strain. Hooke's law. Hooke's law. According to this law, stress is proportional to strain. Stress is proportional to strain, or stress is equal to some constant C into strain. Stress is equal to some constant C into strain. Stress is force by area. Stress is normal force by area. So strain is E by L in the case of longitudinal strain, theta shearing strain, delta V by V bulk strain. Stress is F by A and strain is E by L theta delta V by V. The constant C is given different symbols and names, depending on the form of the nature of stress and strain or the nature of deformation. It is given the symbols Y, N, K. Y for longitudinal stress and strain. C is given the symbol Y, N, K. The relation between longitudinal stress and longitudinal strain is F by A is proportional to E by L and the constant is given as Y. Hence, the relation becomes F by A is equal to Y into E by L in the case of longitudinal stress and strain. That is longitudinal deformation. In the case of longitudinal deformation, F by A is equal to Y into E by L. In the case of shearing stress and strain, F by A is equal to N theta. N is known as rigidity modulus, Y is known as Young's modulus. So C is known as modulus of elasticity. C is known as modulus of elasticity and Y is Young's modulus and N is rigidity modulus. In the case of bulk stress and strain, F by A is equal to K into delta V by V. F by A is equal to K into delta V by V. F by A is equal to K into delta V by V. Young's modulus. Young's modulus is longitudinal stress by longitudinal strain. So Y is equal to F by A divided by E by L. That is equal to FL by AE. Y is equal to F by A divided by E by L. That is equal to FL by AE. Or Y is equal to mgl by pi r square E. F is restoring force. Its magnitude is equal to deforming force mg. Hence, Y is equal to mgl by pi r square E. Area of cross section is pi r square. So the relation for Y is mgl by pi r square E. Rigidity modulus N is equal to tangential stress by tangential strain. Tangential stress by tangential strain. So N is equal to F by A divided by theta. F by A divided by theta, or N is equal to F by A theta. N is equal to F by A theta. Bulk modulus K is equal to volume stress by volume strain. Volume stress by volume strain. So K is equal to F by A divided by minus delta V by V. Minus delta V by V. I will explain why I have taken minus sign here. So K becomes equal to minus PV by delta V minus PV by delta V, since pressure P is equal to F by A in the case of bulk deformation. So F is equal to minus PV divided by delta V. In the case of longitudinal stress and strain, as the stress is increased, the elongation will also increase, so the strain increases. In the case of shearing stress, as force increases, the deformation theta will also increase. Here, in the case of bulk modulus, bulk stress, when the pressure is increased, the volume of the body decreases. So V bears an opposite relation to the applied pressure or force. Hence, to indicate this opposite nature, we have introduced negative sign. In the case of bulk strain, we have introduced this minus sign to indicate that pressure and volume, they are inversely proportional. As the pressure increases, the volume decreases. This nature is indicated by the negative sign. Poisson's ratio, it is indicated by sigma. Poisson's ratio is defined as lateral strain by longitudinal strain. Poisson's ratio is defined by lateral strain by longitudinal strain. Now let us try to understand these two strains. In the right side figure, you notice two cylinders. One is of radius B, the other one is of less radius and more length. In the first case, take the bigger cylinder of more radius. Suppose it is a rubber cord and its length is L. When it is elongated by pulling in the upward and downward directions, if it is elongated, let us suppose the increase in its length is E. Small e represents the increase in length of this rubber cord, and delta B represents the decrease in radius of this cylindrical rubber cord. So E is increase in length and delta B is decrease in radius. Original length is L and original radius is B. Now let us calculate the strains. The longitudinal strain is E by L. And the lateral strain is delta B by B. Hence, the Poisson's ratio sigma will be equal to delta B by B divided by E by L. Sigma is equal to delta B by B divided by E by L. That is equal to delta B into L by EB. As the length increases, the radius decreases. So these two strains have opposite nature. If one increases, the other decreases. This nature is represented by the negative sign. So sigma is equal to minus of delta B by B divided by E by L. Hence, sigma will be equal to minus delta B into L by EB. Minus of delta B into L by EB. This is the relation for Poisson's ratio. The value of sigma. Theoretical value of sigma lies between minus 1 and 0.5. Theoretically, it is derived that its value lies between minus 1 and 0.5. But practically, it should lie between 0 and 0.5. Generally, its value is obtained between 0.2 and 0.4. Minus 1 indicates an increase in delta B by B for an increase in E by L. Minus 1 indicates an increase in delta B by B for an increase in E by L. No such body is possible in nature. 0.5 indicates perfectly compressible body. Nature does not permit. Hence, these two limits are impossible to attain.